All right, so I think this is the hardest material of the chapter on solving trig equations, and we started it last time, but we need to finish this. This is the last material for the next test, which is a week from today. On Wednesday, we'll primarily review, but today I want to see if we can finish this off so I don't have to do any more on Wednesday. And the first thing we said, the easiest problem, maybe we should put this in steps too. We start off with the easiest problem, then we move to harder problems. Suppose I want to solve an equation that consists of trig function equals a number, right? We can solve it on the unit circle if you just remember that. Suppose I want to solve sine theta equals square root 2 over 2. What do we say?
Pi over 4, 3 pi over 4.
Okay, yeah, because we sine theta is the y coordinate. You can do this in your mind even. Once you've done a few of these, you can kind of sketch it in your mind. But you sketch the unit circle on paper in your mind, and you say the y coordinate has to be square root 2 over 2, which is about 0.7, somewhere here. Here is all y coordinates square root 2 over 2 is this horizontal line, right? Y equals a number is a horizontal line. This horizontal line, it will intersect the circle since it's not up to the top in exactly 2 places. That leaves exactly 2 terminal rays that will give sine theta equals square root 2 over 2. Now, if I restrict this and I say solve for theta within one rotation for now, so between 0 and 2 pi, that only leaves 2 angles. If I don't restrict it, then I can go around 27 times and then go to one of these. I'll have an infinite number of answers, right? But there's 2 angles that have these terminal rays within one rotation. One, I rotate to here and I say this could be theta. Wonder what that theta is. And you got it. Or it could be this theta. And how do I find out what they are? I can drop a perpendicular in the unit circle just like we did before, right? If this goes up to y equals square root 2 over 2 from the x-axis, then this side length is square root 2 over 2. Since it's a unit circle, that's 1. That forces this to be a 45, 45, 90 triangle. Theta here must be pi over 4. Right? Similarly, this triangle over here, you drop it at square root 2 over 2, and this is 1. It's always a congruent triangle, the other triangle that you form by dropping a perpendicular. So this is also a pi over 4 angle. But that means the angle we're interested in is pi back up pi over 4 is 3 pi over 4. So there's 2 solutions to this, right? And on the test, maybe you get one of them because you can say, oh, it's arc sine of square root 2 over 2. No, it's not. This one is arc sine square root 2 over 2, but there's another one, this one, pi minus arc sine square root 2 over 2. So there are 2 answers. Theta could be pi over 4 or 3 pi over 4. That's excellent. You can visualize it already. But you start to be able to picture these things in your mind. That's A. Now B, suppose it's cosine theta equals a number. I can sketch the unit circle. And now cosine is the x coordinate, right? So I want all x coordinates square root 3 over 2. Well, that's like 0.87 or something like that. It's almost 1. So I'll go out way out here near 1 just to make it, look sort of like it's supposed to be. And these are all coordinates x equals square root 3 over 2. And I notice this intersects the circle in 2 places. So there's this terminal ray or this terminal ray. And again, if I'm solving for theta within 0 to 2 pi, there's only 2 angles then that can go with the 2 terminal rays. There's this one here. And there's this one all the way around here. And what are those? Well, drop the perpendicular. And since the x coordinate is square root 3 over 2, right? It's on this line. This side of the triangle must be square root 3 over 2. This side is 1. It can only be a 30, 60, 90 triangle. This won't have to be a half by the Pythagorean theorem. So this is a 30-degree angle, pi over 3. And then by symmetry, the other triangle is always congruent. This angle must pi over 3, pi over 6, sorry. This one also must be pi over 6. Which means that the angle we're interested in, this one all the way around here, we can't take this one because it's the negative angle, not between 0 and 2 pi. We'll say it's this one. It's 2 pi back up pi over 6. 2 pi less pi over 6. Well, that's 12 pi over 6 minus pi over 6 is 11 pi over 6. There's two answers to this one, pi over 6 and 11 pi over 6. And if we took the arc cosine, we just get pi over 6, but there's another angle, it's the one down here, 2 pi minus arc cosine. So that one has two solutions. Then tangent is the hardest one. Maybe I should leave more room. Something so optimistic. Let's put it up here. See, we can have tangent theta equals -1 and solve for what angles theta have tangent equal -1. Remember how to do tangent or cotangent, the hard cases? You can do it another way if you like. Rewrite it as a ratio, -1/1, and then divide top and bottom by the root sum square of those two numbers. -1 squared plus 1 squared is square root 2. If I divide the top and bottom by square root 2, I will get a point in the unit circle. -1 over square root 2 for y, plus 1 over square root 2, dividing the bottom by square root 2 for x. And this will be a point on the unit circle. Or I can put the minus with the bottom one and call this 1 over square root 2 over -1 over square root 2. And this could be y and this could be x. But that's what you do. And these are the 2 points on the unit circle that have tangent equal -1. And so then you say, well, that's this one here, -1 over square root 2 plus 1 over square root 2 gives this point here. And then there's the opposite direction, it's always opposite, where I have 1 over square root 2 and -1 over square root 2. And I can figure those angles, right? Again, I drop the perpendicular in all cases here. This goes up to 1 over square root 2, and this goes left 1 over square root 2. So that's a 1 over square root 2, 1 over square root 2, 1 triangle. Oh, it's a 45, 45, 90, right? This 1 over square root 2 is also expressible as square root 2 over 2 by rationalizing by top and bottom by square root 2. And this is a 45, 45, 90 triangle. Evidently, this is 45 degrees, pi over 4. And by symmetry, so is this. So the two angles I'm interested in are pi back up pi over 4, that's 3 pi over 4. And 2 pi back up pi over 4, that's 8 pi over 4 less pi over 4 is 7 pi over 4. Now, I said that pretty quickly, so let's see if there's maybe some questions. But that's how you do those kind of problems, and I'm going to ask something like that on the next midterm. That's a real basic trig problem that you have to be able to do in your later classes if you take more classes where you solve trig equations. Is that clear what you do? Sine, you've got a horizontal line, y equals a number, and you find the two terminal rays and figure the angles. Cosine, you've got a vertical line, x equals a number, you find the two terminal rays and the angles that go with them. Tangent, you write it as a ratio, divide by the root sum squared, you get the point on the unit circle, and then you can find these other things. Now that's case 1. Trig function of a number of theta equals a number. And then we did one more thing, hopefully you remember. I don't want to repeat too much here, but this really takes some practice on this. For a multiple angle, multiple of theta, first substitute, then solve it using 1. Substitute to get a single variable, single angle, theta, and solve by 1. Method 1 for all angles. Then throw out angles not between 0 and 2 pi. We'll say in the desired range, which is usually 0 to 2 pi. So there's a problem here. Here's one of your homework problems. This is number 8. 2 sine of 3 theta equals square root of 3. How about that? Square root of 3, sorry. How do I solve that? I first substitute whatever my favorite letter is, u equals 3 theta. So I got a single angle, right? And I write this equivalently as 2 sine u or phi or whatever letter I like equals square root of 3. Write it as trig function equals the number. So I'll say equivalently, this equation is sine u equals square root of 3 over 2. Now this is trig function of a single angle equals the number. I can solve on the unit circle, right? So if I want by method 1, I'll say, here's the unit circle, and I can say sine u is the y coordinate. Way up here is square root of 3 over 2. Here's all coordinates y equals square root of 3 over 2. I have exactly 2 terminal rays that yield that y coordinate on the unit circle. If I then drop the perpendicular and construct the right triangle, y is square root of 3 over 2 here, so this side must be square root of 3 over 2. This is 1 because it's a unit circle. I recognize the 30, 60, 90 triangle. This is pi over 3, right? 60 degrees. So you substitute u equals 3 theta to get a single angle. Solve it in the unit circle as before. And now this one over here, now let's say it's pi back up pi over 3. Right? This angle by symmetry is the same, pi over 3. So this angle here is 2 pi over 3. Less pi over 3. And this angle here is pi over 3. Now what I deduce from that is the solutions for u are u equals pi over 3 or 2 pi over 3. Those are all the solutions within one rotation. But that's not good enough for this problem. How do I get all angles u?
Plus 2.
Yeah, plus 2k pi. 2 pi times k. It's k rotations, if you like. K can be negative too. It can be negative rotation. So any integer number of rotations, k, these are all all the angles that have these terminal rays, right? There's only 2 terminal rays, but an infinite number of angles that give those 2 terminal rays. These are all solutions u. Where u is any integer, or where k is any integer. It can be 0, 1, minus 1, 2, minus 2, etc. But I'm not interested in u, I'm interested in theta, right? And u is 3 theta. So let's put 3 theta equals that. If these are all solutions 3 theta, I divide through by 3 and say equivalently, theta equals, we'll divide the whole side by 3, pi over 9 plus 2k pi over 3. Or this divided by 3, 2 pi over 9 plus 2k pi over 3. There's all solutions theta. But we don't want all solutions theta. We want theta between 0 and 2 pi in these, right? If I restrict this and I say in this problem I want theta between 0 and 2 pi, what do I get? Well, I just try different values of k and keep all the ones that give me something between 0 and 2 pi, because these are all the solutions. I just have to find the ones that are between 0 and 2 pi. And what happens is when you're dividing by 3 here, there's always 3 solutions. So I'll take k equals 0, 1, and 2 and get all solutions here. So 4k equals 0, 1, 2. I get 3 solutions on this one. Pi over 9. Pi over 9 plus 2 pi over 3. Plus, yeah, when k equals 1 this time, 2 pi over 3. And when k equals 2, pi over 9 plus twice 2 pi over 3 is 4 pi over 3. So those are all the solutions in the first case. And then in the second case, I can get 2 pi over 9 when k equals 0, because you're adding nothing. 2 pi over 9 plus 1 times 2 pi over 3. And when k equals 2, it's 4 pi over 3 I'm adding. 2 pi over 9 plus 4 pi over 3. Then you got to do some fast quotients here. But those are all the solutions between 0 and 2 pi. If you take k equals 3, then you're adding 3 times 2 pi over 3. You're just adding 2 pi to a positive angle. You get something bigger than 2 pi, and it's too big. So k equals 0, 1, 2 will give you all the angles here that are between 0 and 2 pi. K equals 0, 1, 2 here will give you all the angles that are between 0 and 2 pi in the second group. So we've got that, and now we just reduce it with fractions multiplied by pi. Pi over 9 is the first one. Well, let's see, this is 6 pi over 9, and 1 pi over 9 is 7 pi over 9. Have to do these, right? 4 pi over 3 multiply top and bottom, that's 12 pi over 9 plus 1 pi over 9 is 13 pi over 9. So that's that one. And then this one, 2 pi over 9. 2 pi over 3 multiply top and bottom by 3 is 6 pi over 9 plus 2 pi over 9 is 8 pi over 9. And then finally, when in this case, oops, this is 4 pi over 3, wasn't it? 4 pi over 3. Multiply top and bottom by 3 is 12 pi over 9 plus 2 pi over 9 is 14 pi over 9. There's all the solutions. There are actually 6 solutions to this one. Can you do that for the test? So, all right. Questions on that one? That's a harder problem, isn't it? I had, it was 2 sine 3 theta equals square root of 3 was the original problem. 2 sine 3 theta equals square root of 3. To solve this, you put u equals 3 theta, divide by 2 to write sine u equals the number square root of 3 over 2. Solve it as before in the unit circle, but then put plus 2k pi and drop the extra angles that aren't between them. All right, so that's the next hardest one. Now we're going to move up a little bit more. Let's do this one. This would be 3. 4 equations, a number times trig function of theta squared plus b times a trig function of theta, the same trig function of theta, plus c equals 0, where a, b, and c are numbers. How can we solve an equation like that? This is not the only kind of trig equation you get, but it's real illustrative. It gives you an idea how to solve other trigs. How would I solve that? I got an idea. That looks just terrible. Now you have a trig function squared and a trig function and a number. What you do is this, let u equal the trig function. See? To get from this, equivalently, a times u squared plus b times u plus c equals 0, which is what kind of equation? What kind of equation is that? A squared plus bu plus c equals 0. That's a quadratic equation, right? So you can convert this horrible looking trig equation into a quadratic equation. Remember how to solve quadratic equations? You have to know it for this test. I'm going to make you learn it. Quadratic equation can be solved different ways. Number one way to solve a quadratic equation.
See.
We can find u y. One way is to try factoring. If you can factor this thing, you can use the zero product property to solve it. Or if factoring is difficult, there's something that always works. What's another way?
Quadratic formula.
Yeah, awesome. There you go. You can use the quadratic formula. Always works, never fails. Even if there's no solution, it will tell you there's no solution, right? And there's a third way called completing the square. We're not going to do that for the reason that completing this, the quadratic formula is the formula that you get by completing the square. So who wants to do the extra work? So most people memorize this one. So we won't do completing the square here. It's a useful algebra technique that we won't need. All right, so we'll use these two methods to find u, right? And then what do we have? This can have, remember how many solutions can the quadratic formula tell you this equation has?
2.
It can have 2 or 1 or none, right? This gives 0, 1, or 2 solutions. And for each solution that you have, 0, 1, or 2 solutions for u. For each one, you put back the trig function and solve the trig function equals that number, right? Put back or rewrite it as trig function equals first. Whatever trig function u is. Trig function, FCN is abbreviation for function, equals each number. And solve on the unit circle by 1, right? Or 2. If you have a multiple angle. So you use method 1 or 2. I told you last time we did that, like Jack built everything builds on top of each other. But that's the whole thing to solving these complicated equations where you have essentially a quadratic equation and a trig function. Let's try one of these because these are on your homework. 4 sine squared is number 6. I have 4 sine squared theta minus 3 equals 0. Right? And I'll say solve for theta between 0 and 2 pi. I'll use x instead of theta. I just like theta for an angle. Solve for theta in the interval from 0 to 2 pi. How do I solve it? I recognize it's a times trig function squared plus b times trig function. You can think of 0 times sine theta plus c equals 0. So this is your c, and this is your a. But see, this is a quadratic equation with b equals 0. Right? So whenever we see this trig function squared, we'll let u equal the trig function. And this gives us 4 times u squared minus 3 equals 0. It's a quadratic equation. How do I solve that one? Yeah, quadratic formula works every time. This one I'm going to factor though. I want to illustrate factoring too, just in case you want to try that, even though the quadratic formula works every time.
Do you then add the 3, divide by the 4, and then square root it?
Yeah, you could do it that way. I was going to say factor it like this. Your ways right too. 2u plus square root 3. The reason I do factoring is often faster. All right, so when you see it obviously, then you factor instead of using the quadratic formula. 2u minus square root 3. What am I doing? I'm using this formula that says a squared minus b squared is a plus b times a minus b. That factoring formula, right? So I think of this as a square, a squared, and this is b squared. Then b is square root of 3 and a is 2u, right? So that's what I did here. And I factor it, obviously, 2u plus square root of 3 times 2u minus square root of 3 equals 0. The other reasons besides that this is faster is that lots of books will do it this way. You go into your physics class or something, it'll do this and you say, where'd that come from? Why didn't they use a quadratic formula? Because a lot of people like to do it this way, all right? So you want to be familiar with other people's methods too. Now, once this product is 0, what do you know? This is called the zero product property. You take two numbers, a and b equals 0. What do you know about a and b?
One of them is 0.
Yeah, at least one of them is 0, right? Product is 0 and only if one is 0. So the zero product property says either this equals 0, 2u plus square root of 3 equals 0, or this one equals 0, or both, right? Or 2u minus square root of 3 equals. Now these are easy to solve. This one I subtract square root of 3 and divide by 2. I got u equals minus square root of 3 over 2. Or this one, if I add 3 square root of 3 and divide by 2, u equals plus square root of 3 over 2. Right? But I'm not done because u was the dummy variable that I introduced. So I'll put that now. U was sine theta, so I'll write equivalently, this is sine theta equals minus square root of 3 over 2, or sine theta equals plus square root of 3 over 2. See how that works? And now I have trig function equals a number, right? I go back to method 1. I can solve each of these. Solve by method 1 on the unit circle. Method 1 is the unit circle. So I put to the first one and I say this is the y coordinate equals minus square root of 3 over 2. Way down here. I figure the two angles. What are they? Oh, that's not so bad, right? You drop the perpendicular and say, well, it went from 0 down to minus square root of 3 over 2, so this side length must be square root of 3 over 2. Right? This is 1, it's a unit circle. Pythagorean theorem will force this to be a half. This angle is pi over 3. Or if you counterclockwise. So pi over 3 is this angle here. My symmetry, this one is always the same, pi over 3. So what are my angles that I have here? Well, if I'm looking for angles between 0 and 2 pi, I should have put that up here. Oh, yeah, good, that's fine. Then I take one angle that goes around to here. Evidently, theta is, let's see, pi plus pi over 3 is 4 pi over 3. Then the other angle is to go all the way around to here. That's 2 pi back up pi over 3, right? 2 pi and then back up this pi over 3. So this one is theta equals 2 pi left pi over 3. Well, this is 6 pi over 3 minus pi over 3 is 5 pi over 3. So there's the two solutions for this first half. 4 pi over 3 and 5 pi over 3. But I'm not done, right? How tricky this is, I told you this will be the hardest thing in the chapter. Usually the last section is, right? You just get more and more bummed out as you go through the sections, but pretty soon a new chapter comes, right? And then it gets a little easier for a while. I'm gonna erase this one. So that was the first case. Now I have to solve sine theta equals plus square root of 3 over 2. So I draw another unit circle for this case. I draw since sine is the y coordinate, I draw the line y equals plus square root of 3 over 2. And if I'm clever, I can figure this out almost instantaneously, right? What do you think this angle is?
Pi over 3.
Yeah, this was minus pi over 3 going down to minus square root of 3 over 2. This must be plus pi over 3 coming up here, right? And by symmetry, this is also pi over 3. I can observe that I have pi over 3 and pi back up pi over 3 is theta equals 2 pi over 3. I'm sorry, pi over 3 is 2 pi over 3. Here there are four solutions, two from that circle and two from this circle. Here's what you do when you get a sine squared plus b sine plus c equals 0. You can factor, get sine theta equals two different numbers, and solve each one on the unit circle. Okay, now let's see. Now we want to step it up one more here. There we go. Let's deal with cosine this time also. Can I erase this? Is this okay? Yes. I can erase the other side, but I just can't see the screen as well. So this problem is number 11. And it says, suppose 2 cosine squared t minus cosine t equals 1. All right. Suppose I say solve this on the, or theta, I should have said. I like theta better. Solve for theta between 0 and 2 pi. But wonder what the solutions are to that. Now, this one is clearly a cosine squared plus b cosine. Oh, but c's on the wrong side. You better be careful. Right? What I do is when I see a trig function with a square in here, I let u equal the trig function, cosine theta, right? And this gives an equivalent quadratic equation, 2u squared minus u equals 1. And now this time, maybe I want to use the quadratic formula. So solve by quadratic formula, I can say u equals minus b plus or minus square root b squared minus 4ac all over 2a. I hope that looks familiar. Have to have it for the next test in a week. Okay. When you have au squared plus bu plus c equals 0. These are the two solutions. And remember what happens? If you get a square root of a negative, what happens?
It squares out, makes it even.
It means there's no solution, no real number solutions. You have imaginary solutions, right? So if it's square root of a negative, there's no solution, 0. What if this b squared minus 4ac is 0? Then b plus or minus 0 over 2a gives just one solution, right? You can add 0, subtract 0, it's the same thing, there's one solution. So I'll remind you of this discriminant, b squared minus 4ac. If it's less than 0, then you get no solution. If it's equal to 0, you get one solution. But if it's greater than 0, then b plus the square root and b minus the square root, two different numbers. And so if it's greater than 0, you get two solutions. That's how you know how many solutions you have out of here. And you just write them down, right? Now, what are they? Here's what I'd be tempted to write. U is equal to minus b. Let's see, b is, let's put these in here. Here's a and here's b. B is minus 1, so this is minus a minus 1, plus or minus square root. B squared is minus 1 squared, minus 4 times a is 2 times c 1, all over 2a, 2 times 2. Now I'm going to get the wrong answer. Why? What did I do wrong? This is the drawback in the quadratic formula. You have to put it with 0 on the right or it doesn't work. I have 1 on the right, but I called this c equals 1, but it's not c, right?
You have to subtract the 1.
Yeah, subtract the 1 over. So let's subtract the 1 over and say equivalently, putting in one more line, this is 2u squared minus u minus 1 equals 0. Now evidently a is 2. B is minus 1 and C is minus 1. So over here, this is the correct quadratic formula, but I have to get 0 on the right-hand side. So instead of 1 here, I should have had minus 1. There's the drawback of the quadratic formula. You just have to make sure you get it in the right form. Then it always works. So let's see, I've got minus or minus 1 plus 1 plus or minus square root. 1 squared plus 8 is 9. And then all over 4. 1 plus or minus 9 over 4. Those are all the solutions. And there's, since it's discriminant, 9 is positive, I'm gonna get two solutions. One for plus the square root of 9, one for minus the square root of 9. Let's say this is 1 plus or minus 3 over 4. So if I put the plus sign, I get 4 over 4, that's 1. If I put the minus 1, I put minus sign, I take 1 minus 3 is negative 2 over 4, and negative a half. So these are the two values that you can be that satisfy this equation. Those are the only two values for u. Now you go back and put back that u is equal to cosine theta. Hence, either cosine theta equals 1 or cosine theta equals minus a half. Those are all the solutions. This is completely, this first equation here, you see what we did? It's completely equivalent to these two equations. Trig function equal to number, and now we can solve on the unit circle by method 1, right? So solve on the unit circle. Method 1. And this is a good one here, cosine theta equals 1, because that says x coordinate equal 1. What are the solutions to that? If I want theta to be between 0 and 2 pi. X equals 1 is this line that's just tangent to the unit circle, right? So it actually only touches it in one place instead of two. There's only one possible terminal ray. It's this one right here at 0. So the solution here is theta equals 0. Only one solution. Since I put strictly less than 2 pi, don't include 2 pi. Be careful on the instructions whether it includes 2 pi or not. 2 pi would be another one. And now similar over here, cosine theta equals minus a half. That's x equals minus a half. This one's going to be the vertical line right here, right? Halfway between x equals 0 and x equals minus 1 is the line x equals minus a half. It intersects the unit circle in two places, right? Leaving me two terminal rays, this one here and this one here. And now if that's the line x equals minus a half, then when I make the triangle here, this side must be a half, right? I went from 0 to minus a half, it's 1/2 unit long. This is 1. I recognize it's a 30, 60, 90 triangle, right? This must be pi over 3. I go from 0 to minus a half, so that's a half. That makes that angle pi over 3. By symmetry, this is also pi over 3. So what are the angles? Pi back up, pi over 3. Yeah, 2 pi over 3. Make pi back up, pi over 3, and then
4 pi over 3.
yeah, pi plus pi over 3 is 4 pi over 3. Awesome, you got it. So there's three solutions: 0, 2 pi over 3, or 4 pi over 3. It's getting tricky, isn't it? Okay. Here's another one. This is 16. Now they throw a few curveballs at you because in practice, although you can classify all these kinds of problems, and these are the major ones I want you to know, be able to solve trig function equals a number, be able to solve a quadratic equation in a trig function, be able to do it when there's a multiple of an angle, not a single angle. There are some additional tricks for tricks, I guess I could call them. Sometimes we need to get an equations of this form. Try to get one or more of cases 1, 2, 3. Sometimes you get more than one. Here is number 16, which is a real good example of it. It's simple, but it illustrates the point. Suppose I want to solve 4 sine 2 theta equals 4 cosine theta. Be glad you came to class for this one, so you don't fluster this weekend or something. Sometimes you can guess these angles by plugging in. This one you might be able to guess some of the solutions. How can I solve that? There's a bunch of ways, and some of them are a little dangerous. One thing we could do is divide by 4, right? Just call that sine 2 theta equals cosine theta, right? All right. Now what can I do?
Subtract cosine theta.
Could, it won't help me yet. I want to do something first. Whenever I have more than one angle here, I need to get one angle, just like when we were simplifying before, right? How can I replace sine 2 theta in terms of theta?
I was gonna say. I was gonna do divide by cosine, that way you can get tangent.
Here's the trick. When you see a sine of 2 theta, use a double angle formula. So if you see 2 theta in here, rewrite this using the double angle formula. Sine 2 theta is 2 sine theta cosine theta. So it's this double angle identity to get rid of the extra angle. Now I have just one angle. That's why I say this is a curve. You first have to get it so it has one angle, one of those other 3 cases, equals cosine theta. And there's even another curve to come here. You know what a really easy thing to do is? Say, oh, this is equivalent to, I'll write this down because it's wrong. 2 sine theta equals 1. Divide through by cosine theta. It's all solutions to this. Why isn't that right? To divide both sides by cosine theta. Answer is I've eliminated some solutions that way, at least one solution. You can take in any equation, you can divide both sides by a non-zero number. If I have x squared equals x, I want to solve this. I don't divide both sides by x. What happens if I do? I get x equals 1. I get one solution, but I've lost another solution, x equals 0. So that's not all the solutions anymore. You divide through by x, you've assumed x isn't 0, right? You've thrown that case out. So instead what you do is you write this as x squared minus x equals 0 and factor, right? Factor this is x times x minus 1 equals 0. Oh, x equals 0 or x equals 1 are both solutions, right? So that's what you do. Don't divide through by something that might be 0. You can if you then check the extra case that x equals 0 separately. So you can divide through by 0 and check 0 separately, or you just do it this way and factor. I'll do it that way. This is the way more.
So then we just subtract by cosine theta.
Yeah, so instead of doing this, I'm going to subtract cosine theta. Good, yeah. So I'll rewrite this as, so don't divide by cosine theta, instead subtract a factor. 2 sine theta cosine theta minus cosine theta equals 0. That's the trouble. The machine is terribly unforgiving, right? If you divide through by cosine theta, get 2 sine theta minus what equals 1, and solve that, I might give you half credit on the test because you got half the answers. But the machine is going to say wrong until you get everything perfect, right? So on the homework, it's going to give you 0 credit once you do that, and you're going to always wonder what happened. Now we can do this. We're going to factor because we know there's a common cosine in here. Rewrite this as cosine theta times 2 sine theta minus 1 equals 0. And use the 0 product property, right? This product equal to 0 says either cosine is 0, or equivalently, cosine is 0, one of the factors. Factors are things that are multiplied together. So this is a factor and this is a factor, and their product is 0. Right? So factors, things that multiply together. Cosine theta equals 0 to make the product equal 0, or 2 sine theta minus 1 equals 0 makes the product equal 0. This is an equivalent equation. So this equation here is equivalent to these 2 equations. Once again, I'll go to 2 unit circles and between them get all the solutions. Like I said, a machine will give you nothing for everything but a minus sign. It's very frustrating. I'm working on the machine on homework. All right, cosine theta equals 0. This is x coordinate equals 0. So what I do is I make the vertical line of all coordinates x equals 0. Well, that's just the y-axis, right? Here's the line x equals 0. And I notice there's two solutions. Notice I picked some really, all the different cases for you just to make your life harder. No, make sure you learn it. All right, so here's one answer. It's this terminal ray, which is theta equals pi over 2, right? Here's another terminal ray, this one. Theta equals pi plus pi over 2 is 3 pi over 2. So that's all the solutions to the first case, cosine theta equals 0. Or I could have the second case, 2 sine theta minus 1 equals 0. Well, this one is add 1 divided by 2. Is sine theta equals a half. That one is. So this was solving cosine theta equals 0. This is the other equation, which is equivalently sine theta equals 0. I'll do that on the unit circle and say sine theta is the y coordinate. So there it is halfway up. Y is a half. Has two solutions. This two terminal rings, this one and this one. Drop the perpendicular, it's a half unit up, so that's a half. It's a unit circle, and that's a half. This angle is automatically pi over 6, right? Which makes this angle over here also pi over 6. And so from this, I evidently get solutions pi over 6. And pi back up pi over 6 is 5 pi over 6. That 1 minus the 6 is 5/6 pi. And here I've got pi over 2 and 3 pi over 2. In all, I have 4 solutions. Right? 2 from this circle and 2 from this one. Well, this is one of the hardest sections in the whole course. Hopefully I'll be able to get this stuff to the people who maybe couldn't come tonight. All right, can you do that for homework? That is your homework problem right there. They might give you different numbers. All right, so that's the tricks. When you have more than one angle, you want to use your double angle identity or half angle identity to rewrite it with just one angle. Let's see.
Would that one be, the B would be -3, or would it be 3? For, number 19? I just wanna make sure, would that be?
Yeah, B would be -3.
Okay, I just wanna make sure.
Yeah.
5, 1.
So that one's already set up for us, huh?
Yeah, that one's already set with 0 on the right. Now I want to look at one of those two. This is the just the resistance or whatever they call it. I don't know what it's called. Let's do this one. Here is the hardest of the hard, and we'll get this one done, and then you'll be terrific at this subject, right? Not always do you get special angles like this. That happens, right? In general, you solve these quadratic equations or just general equations and trig functions. You don't get a nice angle out of them. What do we do when we don't get a nice angle? We want exact answers. We can write them in terms of inverse trig functions. So this is number 16. And suppose I ask you to solve 5 sine squared theta plus sine theta minus 2 equals 0. All right. What's the first thing I do? Yeah, you use method 3, since it's a sine squared and a sine and constant, let u equal sine theta. To rewrite this as 5u squared plus u minus 2 equals 0. Luckily, we have 0 on the right-hand side. So I read off this is A, this is B, and this is C. Now I'm going to apply the quadratic formula and say immediately u equals minus b is minus 1 plus or minus square root b squared is 1 squared minus 4 times a times c is minus 2 all over 2a. There it is. And I challenge you to try and guess how to factor this. Some of these you really have to use the quadratic formula because factoring is just too hard to guess the factors, right? This is one of the problems. Look what you get, minus 1 plus or minus square root of 1 plus 40 is 41 all over 10. You know what that means this factor is like if you tried to factor it? If these are the two solutions? It means this factors as 5 times u minus one of these numbers times u minus the other one, which would be minus 1 minus square root of 41 over 10. This is how it factors. Who would ever guess to factor it like that, right? When the discriminant b squared minus 4ac isn't a perfect square, it turns out you always get ugly factors like that. And so this is too hard, factoring too hard. When you're stuck, when it doesn't factor, obviously, just go straight to the quadratic formula because you could be spending all day trying to guess minus 1 plus or minus square root of 41 over 2. Right. All right. So there's the two solutions. And now these definitely don't come from a special angle, right? Because now I write u with sine theta. So now we get equivalent to the first equation is these two equations. U equals that is equivalent to sine theta equals minus 1 plus square root of 41 over 2 over 10, excuse me. Or sine theta equals minus 1 minus square root of 41 over 10. All right. How do I solve those? It's still trig function equals a number. You solve it on the unit circle, right? So what is this? What does this look like? If I look at y equals this number. Well, square root of 41 is between 6 and 7, right? Because 6 squared is 36 and 7 squared is 49. So this is a number between 6 and 7. So it's minus 1 plus a number between 6 and 7. So it's like 5 point something on top over 10. So I do have a solution. This is a number between minus 1 and 1. It's like 5 point something over 10. So the y pointer. So it looks something like this, right? Here's y equals minus 1 plus square root of 41 over 10. Right? A little more than a half. Don't have to draw it exact. Just draw it in the top half. Right? Now there's 2 points in the unit circle with this y coordinate. And similarly, this one, minus 1 minus something between 6 and 7 is like minus 7 point something, right? So let's go a little further down. It's like this. Y equals minus 1 minus square root of 41 over 2. And there's 2 terminal rays here also. Right? So 2 terminal rays that give that y coordinate, 2 terminal rays. We're going to get 4 different solutions between 0 and 2 pi. I think this says solving 0 to 2 pi, right? Yeah. Okay. So we'll put it in here. Theta between 0 and 2 pi. And those are the 4 directions. And I just have to find the angles that go with them. So this is the hardest part. How do I find those angles? when they're not special angles. No. Sine theta equals this number. One solution is always theta equals arc sine of this number, right? Inverse sine. I'll take theta equals arc sine. And if the calculator gives me an error, that means this number was bigger than 1 or less than -1. There's no solution. So it's arc sine of -1 plus square root 41 over 10. That's one solution. So what's the other solution? That's this one here. Symmetry to the rescue, right? This must be the same. This angle must also by symmetry be the arc sine of -1 plus root 41 over 10. So the other angle is just pi back up this amount. Pi minus arc sine -1 plus square root 41 over 10. And there's the two on this circle. These are exact answers, just put in terms of arc sine, right? So you can, if you're sending a spaceship to the moon, it can't be off until the 23rd decimal place, right? Then you can calculate 24, 23 decimal places or whatever you need from that. And I'm not sure on the answers, whether they expect decimal answer or if they expect arc sine, I think. Let's see what it says here. I mean, the answers here are given in decimal, so I think they want decimal, but since they put the pin here, apparently you can put in arc sine. I think put decimal on here, but do this on the calculator and put in the decimal answers.
Well, it says round to the nearest 10.
Oh, okay, thank you. Yeah, calculator rounds this to the nearest 10th, all right? So these are exact answers, but run the calculator and round it and get approximate answers then. So that's the hardest one, is actually finding the approximates. And now over here, what are these? Well, this angle right here is what? Since this time I have y negative, if I take the arc sine of this one, it won't be this angle, it will be the angle going like this between plus and minus pi over 2. So this one angle here is this is the arc sine of -1 minus square root 41 over 2, 10, excuse me. Right, that's what this angle is. So what are my two solutions this time? This isn't one of them. Why not?
Because you need 2 pi minus.
Yeah, this is a negative angle. This is a solution to the equation, but it's not between 0 and 2 pi. So I'll take this one. I'll take 2 pi plus this one, which is negative, and I'll get this angle here. So I'll take 2 pi plus arc sine of -1 minus square root 41 over 2, 10. I keep saying it. Gives me this angle right here. 2 pi plus a negative angle is less than 2 pi. And then what about the other one? Tricky, right? Pi plus this angle is actually minus this angle. So it's pi minus arc sine -1 minus square root 41 over 10. Tricky as can be, huh? But this angle is negative. You want to take minus that angle, you get a positive angle here. So you take pi minus this negative angle. There's the four angles exactly, and you can with the calculator round to the nearest 10th. All right, that's it. Now you can do all the problems. But I want to emphasize one more thing. I give you one problem here just to. Can I erase this? Do you want to do any details? Like I said, that's the hardest one. Maybe the hardest problem of the semester, I think. So if it's too scary, it's good time for Halloween. Yeah. I had to make the test sound intimidating. All right.
Okay, go to shareholder of this equation.
So now there's only one more kind of problem on here that's not so hard. I think it was the last one. I'll get it back. Okay. So here's the last one. In fact, I think I didn't do that one. Let me, yeah, all right. So here's the very last problem. It's not as hard, but it is a little different. So 21 says this. Find all solutions. It doesn't say find all solutions between the 2 pi. It says find all solutions, no matter how big, right? To the equation, secant squared x or secant squared theta minus 2 equals 0. This is another quadratic equation. So I can, again, let u equal secant theta this time. And I get u squared minus 2 equals 0, right? It's the equivalent equation in terms of u. And now, I can either use the quadratic formula or factor. I'm gonna factor because it looks easier, right? Think of this as the difference of squares. A squared minus b squared equals 0. It's a plus b times a minus b, where a is u and b is square root 2. There it is. There's factoring, which is faster. I notice immediately now, you don't even have to write this step in. Maybe you can see it before you write this. By the zero product property, either u is minus square root 2 to make this factor 0, or u is plus square root 2 to make this factor 0. 2 cases, right? Become equivalent to the first. All right. I don't know when I've ever bored you. This must be a terribly tiring workout here, yeah. So either u is minus square root 2 to make this factor 0, or plus square root 2 to make this factor 0, so that the product of these two is 0, right? So now I solve it on 2 different unit circles. U recall is secant theta, so I solve the fact of space here first. So equivalently, I have secant theta equals minus square root 2, or secant theta equals plus square root 2 are my two possible things. Oh, look, trig function equals a number, trig function equals a number. Going back to step 1, right? So now by 1, how am I going to solve this? It's secant. We didn't do that tonight. What are we going to do with secant?
The reciprocal.
There you go. Whenever you see secant or cosecant, write the reciprocal equation. Turn it upside down. Reciprocal of the left has to equal the reciprocal of the right, huh? So that's equivalent to cosine theta equals 1 over minus square root 2. Or this one is cosine theta equals plus 1 over square root 2. Taking reciprocals here. There you go. Good.
And kind of the best square root of 2, top and bottom. And
Yeah. And you can write it as minus square root 2 over 2 to recognize the usual form of this. And say, I know what that is, right? This is x is cosine. So I draw the vertical line x equals minus 1 over square root 2, so over here about minus 0.7. Notice there are 2 terminal rays that give you that x coordinate, or meaning both these sides are solution, meaning x can be one or the other or both. I can draw all x coordinates x equals plus square root 2 over 2. And notice there are 2 terminal rays here, this one and this one. How about that? Now what are all the angles? Good one. Well, this went from here to here, from 0 to minus square root 2 over 2. So this side length must be square root 2 over 2. Right? To get from 0 to negative square root 2 over 2. This side is 1 because it's a unit circle. We infer this one must also be, by the Pythagorean theorem, also square root 2 over 2. We don't need to write that. We recognize it's a 45, 45, 90 triangle. This is pi over 4. And by symmetry, this is also.
wouldn't that technically be, well, after everything's thought out, it would be pi over 8 for A, and then B would be 2. So,
Not sure where the pi over 8 came from.
well, we would still have to do the plus 2k pi.
Oh, you're getting ahead of me here.
Yeah, sorry.
Okay, yeah. So
Sorry.
so this is x. And now, the angles I can get are pi back up pi over 4. That's 3 pi over 4. to this one, or pi plus pi over 4 is 5 pi over 4. Those are the two on this side. Similarly over here, this one, well, if I go from 0 to square root 2 over 2, then this side length is square root 2 over 2. This must be a 45, 45, 90 triangle. That must be pi over 4. And by symmetry, that's pi over 4. So the angles are, let's see, pi over 4 is one of them. The other one is 2 pi back up pi over 4. It's 7 pi over 4, right? 8 pi over 4 less pi over 4. So there's 4 solutions to that one. How about that? So this one's a little easier. It's not got those difficult angles where you have to use inverse trig functions. It's special angles. Okay.
Can you explain why we're supposed to use the reciprocal again?
Oh, because if you put secant theta equals minus square root 2, you don't know how to draw it on the unit circle. So if you write the reciprocal, cosine equals minus 1 over square root 2, you say, oh, cosine is the x coordinate, so I'll make all points x equal minus square root 2 over 2. And then I can figure out what it intersects. Where if I put secant theta equals minus square root 2, I don't know how to find the points on the circle that have that secant. Well, it's just, if I get sine or cosine, then it's x equals the number or y equals the number, and I can draw it as line. Okay, 4 solutions to that one. And now I'm not done yet. I'm sorry. This is the big clincher here. Those are the solutions within 0 to 2 pi. What are all solutions? Because the instruction said find all solutions, not just some of them. Those are solutions for theta between 0 and 2 pi, right? What are all solutions? Oh, you know this one. I know you do. You guys got these before. Solutions. It's just all angles with the same terminal rays, right? These are the only possible terminal rays. These are the terminal rays with one rotation. So we just add all possible rotations to them. All solutions are therefore theta equals, let's see, pi over 4 is one of them, plus 2k pi. 3 pi over 4 is another one. I can add 2k pi. 5 pi over 4 is another one. I can add 2k pi. And 7 pi over 4 is the last one. I can add 2. Here's all 4 of those angles, plus an arbitrary number of rotations. And this is the correct answer, and I will give you full credit for writing that, but really this isn't what your boss wants at work. What is not so good about that, even though it's 100% correct? The answer is it's not simple. Think about what these are. These angles are these. There's one here, one here, one here, and one here. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, 9 pi over 4, 11 pi over 13 pi over. All these angles, easier. You can take any one of those 4 angles. It doesn't matter which one. Let's take the smallest one. It's theta equals pi over 4 plus k times pi over 2. It's pi over 4 plus a right angle plus a right angle plus a right angle. Let k be all integers. And this is a whole lot more compact than that, isn't it? So this is what you really want to see when you do this at work. Even though those are all correct answers, this is the compact way of writing all the correct answers. There it is. Finally, all the solutions to that equation. Infinite number of them, right? So if I say find all solutions, you put plus 2k pi in every angle you found. But sometimes it can reduce to right easier if these angles have a symmetry like that. A lot of these problems, you'll find 2 angles straight across. Let's see, it's either angle plus pi, plus pi, plus pi. Then you put plus k pi added to one of the angles. So whenever you have a symmetry of those angles like that, straight across or 4 of them all equally spaced around, you can write it simpler. 2 straight across or 4 equally spaced around, you can write it simpler. All right. We good? That was a rush to get that in. I'm, glad I'm not taking this class. All right, so, that's a good stopping point again. We have a few minutes left. If there's any questions on the list, anything else you want to see? All right, well, why don't you go have a happy Halloween and we'll. All right. Come see me if you have questions, or if you want to ask about anything after class, I'll stay for a while. Thank you for coming in. Take away my cupcakes so I don't eat them all.
Huh?
Take away my cupcakes so I don't eat them all.